Hi guys! For today I've picked out a related rates problem which deals with a ladder that's sliding down a vertical wall, and we're going to find two different missing rates. So the first thing that I always do with related rates problems is draw a picture. So this is one of the ladder problems which you will see a lot of. It's a ladder that's sliding down a vertical wall. There's our wall. And here's our ladder. It's propped up against the wall. And then here's the ground. So here's the 90-degree angle. Now what I always tell students is you can label numbers onto the picture that are never changing. So for example, the 13-foot ladder, I can put a 13 right there because the length of the ladder is never changing. But anything else in the picture that is changing has to be labeled with a variable. So like the bottom, I could label X, and the wall, I could label with a Y. Both of those lengths are going to change because the ladder is moving down, like that, which means the base of it is moving away, like that. So X and Y will be changing. So now that I've got a diagram, I usually make a list of the different numbers that they've told me. So we can just say what we know, and we can scan through the paragraph to see any numbers that they've given. Besides the 13, it says it's sliding down a vertical wall at a rate of 2 feet per minute. Well, that's the rate at which the y is changing. So what we call that is dy dt. And since it's sliding down, which causes that side of the triangle to get smaller, it's a negative rate. So I'm just going to say -2. Don't bother putting the units there. Now, it goes on to say, at the instant when the foot of the ladder is 12 feet from the base of the wall, so what that is telling us is the value of x. So x is equal to 12 at this instant. They didn't tell us anything else, but you probably can notice from the picture that if x is 12, that the y at that instant will be 5, because that's a 5, 12, 13 triangle. So let's just jot down that y equals 5. Now, if you didn't realize that y would be 5, you could always do the Pythagorean theorem and just say y squared plus 12 squared equals 13 squared and solve it from there. Now I'm just going to erase these two things here because they're in our list. We don't need those written on the picture. And that's all that they've given us. Now they're asking for the rate at which the foot of the ladder is sliding away from the base of the wall. So that's what we want. And so it's okay that we don't know this value yet, but that's asking for dx dt, the rate that the foot of the ladder is moving away from the wall. So that's like our question mark. Now, an easy equation that relates all of these variables is Pythagorean theorem. So we can say x squared plus y squared equals 13 squared. And for these ladder problems, that's usually the equation you're going to use. In part B, we will use something else because that involves an angle. But you write down the equation, and then from there, you take the derivative of the equation with respect to time. So this x squared, that's going to be 2x. But then since we're doing this with respect to time, we times by dx dt. And then the y squared, that's going to be 2y times dy dt. And then the other side, 13 squared is just a constant. It's 169. So the derivative of that is just 0. So that makes that kind of handy. Now let's plug in everything that we can. So 2 times 12 was the x. Dx dt we don't know, which is fine because that's what we're solving for. Plus 2, and then the y value is 5. Times, and the dy dt was -2, equals 0. Okay, so I'm just going to simplify this. I'll take it up and over here. So that's going to become 24 dx dt minus 20 equals 0. And then just get dx dt alone. So add 20 to the other side. That's 24 dx dt equals 20. And just divide both sides by 24. And we can reduce that also. So dx dt, that's going to equal, they both divide by 4 evenly. So that'll be 5, 6. And then the final thing is the units. This is the rate that the x is changing. And so that will be measured in feet per minute. In some problems, you'll be dealing with volume, then that would be feet cubed per minute. Or if area is changing, that would be feet squared per minute. But if it's just like the length of a side, like height, radius, x or y on my diagram here, it's just feet per minute. Or whatever other units that they give you in the problem. So that would be the answer to part A. Now the answer to get part B, it's asking for the rate that the angle theta is changing between the foot of the ladder and the ground. Well, what that's talking about, let's just erase this little, get that arrow out of our way. So the theta that they're talking about would be right there. And so nothing else about the picture has changed. All the numbers that they gave us originally are still the same. The answer that we got to part A would still apply to part B. So we just basically need to have a new equation so that we're working with theta. And what I would use, I think I would use sine, because then I could do opposite over hypotenuse. And since the hypotenuse is 13, and it's not changing, that'll make it easier to work with than if you picked, say, tangent. Because if you do tangent of theta, you're going to have to equal it to y over x. And then you're going to have a lot of variables to work with. So I'm going to write down right here, the sine of theta equals y over 13. Okay, now don't let this trip you up. Y over 13, I would rewrite that as 1/13 y. I'm going to move some of this other work. Okay, I just moved some of our previous work out of the way. So now the next step here is to take the derivative with respect to time. So sine theta, the derivative is cosine theta. But then since we're doing it with respect to time, it's times d theta dt. Just think of that step the same way as you did implicit problems. Every time you got to a y in an implicit problem, you would do its derivative and then times by dy dx. Well, this is basically the same thing. Theta, we're differentiating with respect to time, so we write d theta dt when we get to it. And then on the other side, same idea, 1/13 y, the derivative is just 1/13, but since that was a y, we multiply by dy dt. All right, now we plug in everything that we can. We know that d theta dt we're not going to know. We will not know that because that's what we're solving for. 1/13 dy dt was what we had before. It's times -2. That was from part A. And then, so the last thing to fill in is this, the cosine of theta. Just look at the triangle. Cosine is adjacent over hypotenuse. We know that the adjacent, which is x, right at this moment, we had said that it was 12. So cosine of theta is 12 over 13 because it's adjacent over hypotenuse. And now we just need to solve for d theta dt. So Let's multiply both sides by 13/12, because then I can get d theta dt by itself right here. So this side times 13/12. So if I do that, the 13s are going to cancel. I'll have -2/12, but that reduces to -1/6. And that's the rate that an angle is changing, so that would be radians per, and from the problem we know that time was being measured in minutes. So it's -1/6 radians per minute, which makes sense that it's negative because the angle is getting smaller. Whenever anything in a picture is getting smaller, its rate will be negative. And that is it.